This is readiness check 7 on the K over S feedback loop, which has just been closed and shown here with sizo tool. And we're looking for a bandwidth of 3 radians per second. And that is shown here, where our 3 radians per second comes down right about there. And that's going to give us a closed loop root on the root locus over to the far left. You can see the closed loop root over here to the far left for 3. And so that gives us our crossover frequency, which is equal to 3 radians per second. And we assume that that crossover frequency so this is the system that we have, and we can say that the root locus gain here was in the feedback loop, and of course that's equal to, from the sizo tool, approximately 3, and that gives us a root at 3 as well, and a bandwidth of 3 for this particular system. So we can say that our first loop closure on the inner loop, we'll call it CLTF, or closed loop transfer function, is equal to feedback, and then we had K over S, which was G, and we're feeding it back through a gain of 3. And so our CLTF in the shorthand form looks like 1 over S plus 3. So we're going to take the closed loop transfer function as shown here, and we'll just give it its own little block. Closed loop transfer function block. And then we're going to integrate the output theta dot, and that will give us theta. And we'll feed that back through an outer loop with a gain in the forward section. We'll call that KOL for K outer loop, like so. So our next open loop transfer function, which we'll call, say, OLTF2, is going to be equal to the closed loop transfer function divided by S. Now that's going to end up giving us a pole at the origin, like so, and then this inner loop closed loop pole will become an outer loop open loop pole, and the root locus, of course, is going to come to the center, like so, and meet at the center, and then it'll break away at around 1.5 and go up the j omega axis. We know that's the case because if you recall, if we pick a trial point, then we know that the phasors LP1 and the phasor LP2, we know that the angle of those phasors, if it adds up to 180 degrees, that point is on a root locus. And so this is what our root locus is going to look like. And we can pick whatever damping then we want as we march up with the gain going up the root locus plot if you turn your grid on. So if I go back to MATLAB and create my open loop transfer function form, or in ZPK form, my open loop of my inner loop is going to look like so. So if I sizo tool my OLTF2, we'll see from my sizo tool that once again here are the roots at the origin, and here's the open loop root at -3 and the origin, and they're going to come together. So if I put my finger on them, I can move them with gain, and we want to move them up till we had a gain of points. I'm interpolating between 0.64 and 0.7. And if you look down at the bottom left, you can see that the damping is being written out for me. So 0.7 is going to be right about there or so, 0.71. And I look over here on the right, and I see that my bandwidth for 0.7 is going to be about 1.04. This crossover frequency here would be about it's 1.35. It's listed right here. It's showing to us 1.35. I also noticed from the bottom left that the gain to get this 0.7 closed loop damping and 1.35 predicted bandwidth from the crossover frequency is 4.46. So we'll just say it's 4.5 for now. So we have a gain of 4.5. And so here is the response of the outer loop with an outer loop gain of 4.5. And I've shown you the rise time here from 10% to 90%. The rise time is about 1 second. 1.25 minus 0.25 is 1 second. So it's got a rise time of 1 second. Now the inner loop had a bandwidth of 3. So the time constant for the inner loop, which would be a first order system, would be 0.33 seconds. So the inner loop here at 0.3 seconds will be already at 63% of its final value. And you can see that the outer loop then is considerably slowed down. Let's see what we've done. The inner loop SAS, stability augmentation system, when we closed with a root locus gain of 3 and the inner loop, gave us a closed loop system. The inner loop CLTF with root locus gain of 3 resulted in a closed loop transfer function of 1 over s plus 3. Then we closed the outer loop on the inner loop. So we had the CLTF, which was equal to 1 over s plus 3. And that came out with theta dot. But now we integrated that in order to get theta. And then we fed theta back through an open loop gain, which we have set here to be equal to 4.5 from the root locus plot. So you can see that this second open loop transfer function for the outer loop has inner loop poles at the origin, which comes from this 1 over s, and at minus 3. And notice now that they're open loop poles, because we're going to vary the outer loop gain for this next root locus. And when we do that, we're going to have a root locus gain, which is going to head in this way and then move up the j omega axis, like so, till we have a gain of 4.5. So if I were to feed back my OLTF2, then this CLTF2, my outer loop closure, which I call CLTF2, will be equal to the feeding back the OLTF2 from the inner loop, which was integrated with a gain of 4.5, and feeding that back, you'll get a transfer function of 4.5 over s squared plus 3s plus 4.5. So this Bode plot is going to look 0 dB out to 4.5 and then break down at 40 dB per decade because of the s squared. So if I take the asymptotic Bode plot of the OLTF2, which is the outer loop with a gain of 4.5, and take a look at that, this should be the outer loop gain, and we see I have a bandwidth, which you said about 1.35, 20 dB per decade before that, and then they have a break frequency at 3. And if you close the loop on this, you'll get a second order system that should have a bandwidth of around 1.35 radians per second, since that's the predicted bandwidth from this open loop plot. So let's take a look at that real quick. So here I put the hold on the Bode plot, and then we're going to look at the asymptotic Bode plot of the closed loop system on top of it. And here we have all the plots superimposed. So this line right here that I'm highlighting is the open loop, which crossed at 1.35, then it broke down at 3. And here's the angle for the open loop. The closed loop system has 0 dB, as we expect, 0 dB all the way out to about 1.35, and then the blue line has a bandwidth, I don't know, somewhere maybe even possibly 2 or so, between 1.35 and 2. And we can look at the angle for the closed loop system, which starts out at 0 and hits around 90 degrees, somewhere around 2. So you could take either 3 dB or the 90 degree for the closed loop system and declare that the actual bandwidth. The predicted bandwidth, however, came from the crossover frequency of the open loop system. So that's what we want to get straight here. The predicted bandwidth of the closed loop system comes from the open loop system. In that case, it's in this case, the crossover frequency is 1.35. The actual closed loop bandwidth is shown by this line here, right? And an actual closed loop system would have a 3 dB, approximately 2 or so. And the angle is 2. And the last thing I ask in this quiz is to put your actual actuator in. Now I'm picking a lousy actuator here, 5 over s plus 5. It's got a time constant of 1 over 5, or 0.2 of a second, very slow. So we're going to define a new transfer function in the forward loop that has the actuator. And then we're going to take the old gains that we use. So it says, what's the actuator going to do to our design, basically? If I put a lousy actuator to implement the design, what's going to happen? And the first thing I notice is that if I took the new transfer function with the actuator and fed it back through 3, I'm going to get a second order system. Okay, second order system. So here's a comparison of the original without the actuator. It's 1 over s times s plus 3. With the actuator in, I get a second order system with a damping of 0.7 and the natural frequency of 3.8 radians per second. So there is a change there. So here I've taken the feedback for the new system, fed it back through and then I will integrate that inner loop closed loop transfer function divided by s to get theta, and use my 4.5 gain to create a new OLTF new transfer function. Now if we look at that, if we close the loop on that OLTF new with a gain of 4.5, we can compare it to what we had last time with the SIZO tool. So let's do that and see what happens. And what I see here is that when I close the loop on this system, I'm going to get roots over here, which are at damping is 0.6 now, 4.7, and I don't really even have a phase margin. The actuator, if I put this actuator, which is lousy, into the system, let's see what the step response is going to be for that one to then the one without the actuator. And so here I can see the two step responses. The one with the overshoot and the undershoot is with the actuator, and the one without the actuator is shown in green with the lesser overshoot. Notice also that it starts faster. The one without the actuator starts faster. The actuator has a slower start. In other words, it puts some phase lag into my system. And here's the Bode plot. The green line on top is without the actuator, and the system with the actuator is on the bottom. And we see that, notice how the phase, as we expect, drops 90 degrees because of the actuator. Their phase angles are the same. They're crossover, but there is a loss of gain. So I would have to raise the gain to get the same crossover. And if I raise the gain on the blue curve to get the same crossover as without the actuator, you see I'd have a phase loss here. I'd have a phase loss between the blue and the green, but it wouldn't be much. It'd be only maybe, I don't know, 10 or 12 degrees. So that shows you the effect of putting the actuator. Putting the actuator in the system adds lag. This is phase lag at the same bandwidth, or lowers the bandwidth of the system with the same phase margin. So the actuator, if you take it into design or not, it's probably a good idea to take it into account, at least a reasonable actuator. Or if you don't, realize that if you use a perfect actuator, you're going to have some phase loss when you actually put it into the system. We'll see that the same thing happens when we add our gyro. Alright, this ends readiness check 7.